Good morning everyone. Today in this video we will learn about interference in thin films due to reflected light. A film is said to be thin when its thickness is about of one wavelength of visible light, which is taken to be as 5500 angstrom, or in other words we can say 550 nanometer. In this topic, a thin film, we normally call it as an air film, which is enclosed between two transparent sheets or a soap bubble, or a thin film can also be made up of a glass, a mica. They can also be treated as thin films. There are many interesting examples of interference produced in thin films. Few of them which we normally see in our day-to-day life is when an oil drop spreads on the surface of water, or a soap film when it is illuminated with white light, we now see beautiful colors in it. So how these phenomena arises, or why we see the beautiful colors in the soap film or an oil drop spread on the surface of water when it is illuminated with white light? These phenomena normally occur due to interference in thin film due to refraction of an light, which we will study today. We see over here in this experiment we have considered a glass plate as a thin film whose thickness lies in the visible wavelength range. Here we have considered a ray AB of monochromatic light of wavelength lambda is incident on the upper surface of a thin transparent film of uniform thickness T and having a refractive index mu which is greater than 1. When it strikes on the surface of a thin transparent film at an angle of incidence I, partly it is reflected along the ray BP and partly it is transmitted or refracted along BC. The refracted part BC is reflected from point C on the lower surface of the film along CD, and finally it emerges out along DQ. The ray BP and the ray DQ are derived from the same incident ray, so both the rays, ray 1 and ray 2, are said to be coherent. If the thickness of the film is very thin, then the ray BP and the ray DQ will be sufficiently close to each other and in a position to interfere. In order to evaluate the path difference between the ray BP and the ray DQ, the perpendiculars DH and CN are drawn on ray BP and surface BD respectively. As the path of the rays BP and DQ beyond DN, beyond DH are equal, so the optical path difference between these two rays will be written as path difference is equal to the path travelled by the ray in the medium, that is BC, plus CD in the medium, and minus BH, that is this distance in the air. We know that a distance in air is numerically equal to mu times the distance in the medium, and for air the refractive index is equal to 1, so path difference is equal to mu BC plus CD minus BH. Now in this case we will evaluate the values of BC, CD and BH. So in order to evaluate the value of BC, we will consider the right angle triangle B, N and C. If we see the diagram, this is the angle of incidence I and this is the dotted line is the normal. So if from the dotted line, if I see this angle, this is completely 90 degree. So this is R, so half of this angle is 90 minus R. So my point N will become 90 degree and point C will become as R. So here I want to calculate the value of BC, so I will consider the right angle triangle BNC. So in order to calculate BC, if we will consider the angle cos R is given as base upon hypotenuse. So if I see the base over here, so my base is NC and hypotenuse part is BC. So cos R is NC upon BC. So from here I will get the value of BC, which is equal to NC upon cos R, and NC is nothing but the thickness of the film, which is denoted by T. So I get the second equation as BC is equal to T upon cos R and angle BCN is equal to R. Similarly, in order to get the value of another term in equation 1, that is CD, again I will consider the same process, that is a right angle triangle CND. So in this right angle triangle, I need to get the value of CD, which is my hypotenuse part. So again I will consider the angle cos R, and cos R will be equal to NC upon CD. So CD is equal to NC upon cos R, and NC is nothing but again the thickness of the film, that is T upon cos R. So this is my equation second and equation third, and equation second and equation third gives me the value of BC and CD. Now the third important parameter is left in equation 1, that is the term BH. So now in order to get the value of BH, in this case again we will consider a third right angle triangle, and third right angle triangle we can easily see here is, that is BHD. If we see this right angle triangle, this is my angle of incidence I. So from this dotted line to this whole complete angle, if I say, that is 90 degree. So leftover portion is 90 minus I. So my angle H becomes, that is 90 degree. So I need to get the value of here, I need to get the value of BH. So in order to get BH, here we will consider the angle, that is angle sin I, and sin I is given as perpendicular upon hypotenuse. So if my angle H is 90 degree, so my perpendicular part is BH and hypotenuse part is BD. So sin I is BH upon BD. So BH is equal to BD into sin I. Now again my BD term is completely unknown over here. So I can divide the BD into two parts, that is BN plus ND. So my BH is equal to BN plus ND bracket close sin I. Now again if I see over here, Bn is unknown to me and Nd is also unknown parameter. So same way as we have determined the equations second and third, we will again consider the same right angle triangles, that is BNC and CND. Now in this, again in the same right angle triangles, now I have to get the value of Bn and Nd. So in order to get the value of Bn, here we will consider the angle that is 10R, and if I consider the angle 10R, 10R is nothing but perpendicular upon base. So if my angle N is 90 degrees, so perpendicular component is Bn and base is Nc, so 10R is Bn upon Nc. So my Bn is equal to Nc 10R and Nc is T, that is T 10R. That is, this is the equation 5 which gives me the value of Bn. In the same way, I will calculate Nd, and in order to calculate Nd, again we will consider the right angle triangle CND. Same way, again 10R is Nd upon Nc, that is perpendicular upon base. So Nd is equal to Nc 10R, which is equal to T 10R, which is my equation number 6. I have numbered the equations over here so that it is very easy to substitute the values by naming the equations. So what I will do here, I needed to get the value of BH, and BH was BD sin I, and I had divided BD into two parts, that is Bn plus Nd. So that is my equation number 4. Now I will substitute the value of Bn and Nd, that is equation 5 and 6, in equation number 4. So on substituting equation 5 and 6 in equation 4, I will get the value of BH, and BH is T10R plus T10R into sin I. T10R, that is twice T10R into sin I. Now everywhere we have the angle of refraction R, but here I am getting the angle of incidence I. So using the Snell's law is written as mu is equal to sin I upon sin R. Therefore I can write sin I in terms of sin R, that is sin I is equal to mu sin R. So my BH now reduces to the form of 2 mu t sin square R upon cos R, that is my equation number 7. So at the last, I will substitute the value of BC, which is my equation 2nd, the value of CD, that is my equation number 3rd, and the value of BH, which is my equation number 7, in equation number 1, that is the equation of path difference. So that equation is delta is equal to mu bracket, here it was BC, that is T by cos R, again CD, that is T by cos R, minus BH, and the value of BH is 2 mu T sin square R upon cos R. So this term if I see, that is twice T upon cos R. So I have taken the common parameters over here, and common term is 2 mu T upon cos R. So the parameter which is left inside the bracket is 1 minus sin square R, and 1 minus sin square R is nothing but it is cos square R. So in the numerator I have the term cos square R, and in the denominator I have the term cos R. So one cos R term gets cancelled out. So final part difference I get it over here is 2 mu T cos R. That is my final equation number 8. Now one more thing I need to add it over here is that, as we have seen that you people know very well the Stokes law, and Stokes law of reflection states that whenever a wave of light is reflected at the surface of denser medium, it always suffers a phase change of pi or a path change of lambda by 2. And in our case, that is the interference in thin film of reflected light, we have seen that whenever a beam is falling on the surface of the thin film, that is ray AB, the ray SA falls on the surface of the film, it is partially reflected along BP and partially refracted along BC, and from point C it moves towards the CD and it emerges out as DQ. So if I consider the ray BP and DQ, at the ray BP the ray is reflected from the denser medium surface. So at that particular point we have to add an additional path difference of lambda by 2 or a phase change of pi, because it follows the Stokes law condition as the wave is reflected from the surface of denser medium. So now my final path difference is delta plus minus lambda by 2. Plus minus clearly signifies here you can add it or subtract it, whatever you need to do it, or whatever you need to change it over here. So my final path difference is 2 mu t cos r plus minus lambda by 2. So at the last, now at what point the waves will interfere and give the constructive or destructive intensity. So in order to calculate the conditions for constructive and destructive intensity, we know that for constructive interference pattern, the path difference should be an even multiple of lambda by 2, that is 2 mu t cos r. Here I have considered minus term, I can consider plus term also, it won't make any difference over there. It is completely your choice, you can add it or you can subtract it. So I have considered the minus term over here. So my equation is path difference, which is 2 mu t cos r minus lambda by 2, and this is equal to an even multiple of lambda by 2, that is twice n lambda by 2. So this minus lambda by 2 term goes this side, so it becomes plus. So my final equation is 2 mu t cos r, this is equal to bracket close 2n plus 1 lambda by 2, where n starts from, n is an integer, it starts from 0, 1, 2, 3. So this is my equation number 9, and when this condition at a particular point is satisfied, the film will appear as bright. At what point the film will appear as dark or destructive interference will occur? That is, for destructive interference, the path difference should be an odd multiple of lambda by 2, that is, the 2 mu t cos r minus lambda by 2 is equal to 2n minus 1 lambda by 2. This term can be 2n minus 1 or plus 1. If I am writing 2n minus 1, then the value of n will start from 1, and if I write it over here as 2n plus 1, then the value of n, which is an integer, will start from 0. So final equation is 2 mu t cos r, this is equal to 2n minus 1 lambda by 2, and this minus lambda by 2 will go this side, so it cancels out. So it becomes 2n lambda by 2, where 2 and 2 cancels out, this is equal to n lambda, and n starts from 0, 1, 2, 3 and it goes on. So at whatever point, if this equation 10 is satisfied, at that particular point we will observe the film will appear as dark. Dark means it will be completely dark. So equation 9 and 10, it is clear that the maximas and minimas in the interference pattern due to reflected light depends upon two factors. First is the thickness of the film and second is cosine of the angle r. So here we end the topic, interference in thin film of uniform thickness due to reflected light. Thank you.